unfortunately, the one thing I haven't been able to figure out in terms of this recording is that when somebody tries to call me, even though nobody ever calls me on FaceTime or something, it deletes all the previous recording. Most of the time it just pauses, but for sometimes it does that. So I apologize now that I don't know who that was. Nobody ever calls me, and they usually know not to call me at times like this. So there's these basic elements of how this mathematical system works that just takes practice. And it just takes kind of reviewing your vector calculus and remembering what it means to take a cross product and to take a derivative. To take dui dxi. What is that going to look like? It's a gradient in multiple directions. What is it? Can you just tell me what does it look like in written out?
du1 over dx1 plus du2 over dx2 plus du3 over dx3.
Right. So we are adding these again because the index is multiplied. Whoops. So it's all three of those gradients, and there's another name for that. Does anyone remember what that's called? Does this look familiar? This is just the divergence. And so this symbol that you guys probably all remember from your vector calculus is really just this. dx1 d by dx2 d by dx3. So we don't even have to use that nabla delta system, whatever you want to symbol anymore, because we can write the same thing with just our indices. Same thing.
How does that look, writing it with just the indices?
Like this.
Oh.
So this is the divergence. If, on the other hand, you do dui dxj, what is that? Is this this one ended up, if we add all of these together, is this a scalar vector or a tensor?
Where are you pointing?
Oh, sorry. This one. We calculate those, we add them together, what do we get?
Scalar?
Yeah, just scalar. So we stuff the numbers in here, we get a scalar out of it. Here we have a separate u and a separate I and a separate j. So are we summing over this or not? No, so what is this going to look like here?
It's going to be a tensor.
Yeah, it's going to be a tensor. And the first one will be du1 dx1. And then down here we have du3 dx3. du1 dx3. And you fill in the others. the same thing. So this is the gradient of a vector, because you're taking the gradient in many, the gradient in many directions. It stays as a tensor. The curl, which is that delta function here, cross product with our vector u. How do we write a cross product? Annie, what's the little shortcut way, what symbol do we need to write the cross product at least?
No idea. I'm so
Okay,
lost.
you're so lost, okay. Anybody else wanna?
EIJK.
Yeah, that's where we come back to that EIJK. So the EIJK is what helps us do the cross product. The two vectors that we're going to put in this cross product are our u vector, and then this guy, which is actually also a vector, because it's got, so this del symbol has three components, so it's really a vector. It's also, it's the gradient in each of those directions. So what this ends up looking like, actually, I'm gonna erase this one. D by dxi, and then we have our other u. Actually, I want to do uk. It doesn't. The reason that down there. So this cross product is a cross product between this vector, even though it is a vector, even though we don't usually think about it that way. This vector and the cross product. The cross product is this guy. This expression is our one vector, and then the uk is our other vector. And the reason that I put the k and the j there instead of the I is because that I, when we write out, let me write this out again, E-I-J-K D-U K dxj. This is the cross product where you have some basis function A1, A2, A3. Your next vector d by dx1, d by dx2, d by dx3, u1, u2, u3. Because when we do cross products, we usually have that basis vector as the top. And that's why that is my first index, is that basis vector. The second index is the middle vector, and the third index is the end one. But you can take this, even if you forget how a cross product works, you've forgotten everything that you use, if you take this and you start plugging in 1s, 2s, and 3s and follow the rules, you'll come up with the right answer. So we have two k's here, which means we're going to end up summing over those k's when we write this all out. We have two j's here. That means we're going to sum over the the j's as well. So when we go through our 1s, 2s, and 3s, we're going to have like the E1 JK DUK DXJ is going to be E111 du1 dx1 plus E112 du1, actually du2 dx1. And so for this one, and then it goes on and on. So for this one, I equals 1, j equals 1, k equals 1. This one, I equals 1, j equals 1, k equals 2. And then we can say, well, if we look at our rules, what is E111 equal to?
Oh, so that will be a scalar, you mean? And that will be,
Eventually
that's
you'll
your
add
point.
all of these up, and this becomes a scalar. And that's just the first component of the final vector we're going to get out of this. So we still have this one here, and we'll do the same thing for the E2jk and the same thing for the E3jk. So you end up with 3 values at the end that are the components of the vector in this basis coordinate system. Does that make any sense? But if you write all of this out, so what the rules of this alternating are that it's equal to 1 when I, j, and k go up in value from 1 to 2 to 3, or from 3 to back to 1 to 2. So they're always in that positive, it's circular but positive direction. It's -1 when they're different circular but in the negative direction. So if we go 1, 3, 1, 3, 2, or 3, 2, 1. And it's 0 in every other case. So what's this term going to be?
0.
0. What's this term going to be? 0. So you can write it all out, but you'll find you're just cutting out a whole bunch of terms along the way.
So it is not done yet, right? You still have
No,
other
this is
terms.
just the beginning. It'll be plus dot 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 plus. And then there's the E2jk and E3jk. So what you'll get out of this is a vector and the cross product. What direction is that final vector in? Do you guys remember?
Orthogonal.
Right.
It's orthogonal to both other vectors, yeah. So if you're feeling rusty on some of the vector calculus, it'd be great to just go review some of it, what the divergence is, what the gradients are, and what curls are, how cross products come in. How many of you are feeling super confident in all of that stuff? Okay, so the rest of you that don't feel confident about it, ask those people that are feeling pretty confident about it. And if that doesn't work, then obviously come ask me. But this is where I encourage you guys to work together. The homework has a bunch of just kind of examples to let you play around with these. Write a bunch of them out yourselves. It really is something that just takes practice. So go through some of the examples in the notes, but please, please, please come and talk to me about it if you're still feeling, if you're confused by it. We can do, and I'm going to have you guys do this right now, really quickly. B with the bar on top. So why don't the two of you see if you can write this equation in this notation. The two of you write out this one in this notation. And between the three of you, let me give you another one to add on to that. Do that one, and then what's another good one? Talk to each other.
They're ready to go. Oh, so we're sure which one. So you just want us to put it
Is
in
this an
index
index
notation?
Yeah,
notation?
just
Oh,
write
okay.
it out in index notation. You don't have to write out the ones,
Scalar.
twos, and threes, just in
Yeah.
terms of i's and j's.
So, it will be 2x ij plus ij.
I think kind of thought I understood this coming in, and
So,
now I don't understand it at all.
I'm not sure I'm familiar. It seems the first one is just adding ij to each variable. Am I missing something?
Yeah.
Not necessarily. How do you express x as a vector in index notation?
I see.
You take the bar off, you still get the
Yeah,
x.
just xi.
xi.
Right. Oh, I see. That'll be a j.
So like A.
Well, so this is where you can need
No,
to be careful. If you're multiplying them, yes.
Which I got. Her notes.
Oh, good.
If you were to write out, if you were to actually do this
It's just with
sum,
respect to.
Each of those
Oh,
vectors
those
has an
are
ijk
the
component, right?
no,
Could
it has
be.
a 1, 2, and 3 component.
Mm-hmm.
Okay.
Maybe write them out as vectors with the 1, 2s, and with the, like write it out as three vectors, and then think about how you would add them together.
Hmm? How do you get to it? Yeah.
I mean, that's gonna be that's nice.
Okay.
Just I'm not sure what format she wants us to write it in now.
So the head, the E that
Yeah,
you
I'm
had,
curious
when
now
we
how to-
factor, we'll
Yeah, I'm not as familiar
I
with
didn't-
the
Yeah,
whole
so
I didn't
we
get
have
that is the cross. How does the E actually go? Oh yeah, you switch across U and then. Yeah, okay.
Okay, just take 30 more seconds, and then wherever you are, you are.
It's del.
That'd help in a moment.
No, so it just becomes a and that goes to 1.
I'm gonna have to look into this
I mean, yeah, so the
a little more.
multiplication of the two E's.
It does take kind of an odd thinking initially, but once you kind of get it a bit, you'll. Okay, let's come back together and just wherever you guys are, you are. So what did you guys come up with?
Wait,
The 2 stays.
The 2 stays. All right, that's a good
Okay.
start. Well, so did you write it out like this? X1, X2,
Yeah.
X3?
Yeah.
And then Y1, Y2, Y3. Z1, Z2, Z3. So you got that
Yes.
far, right? Because
Yes.
that's the old way. So if you were to actually do this problem, which components do you add together? What do you end up? How do you,
X1, the ones, the twos, the threes.
right. So Z1 is equal to Y1 plus 2 times X1.
Right.
Yeah.
So we had gotten to the point where
So
you got this far, right? But that's
Yeah.
So 2xi plus yi plus zi.
right.
equals
And now
vi.
do you see why because you said initially yj? How would that get
Yeah.
confusing? Do you see that?
The three vector components 1, 2, and 3. I thought
Yeah.
about ijk. I get it.
No. They're not IGK, and this is definitely
I get
something
it.
that.
So I equals zi.
And by those all being i's, you can immediately see that you're going to take the x1, the y1, and the z1 and add them together. If we had a j here, that would just be really confusing because this is in a coordinate system that's based on I, and the j's would be something. It
This
wouldn't
is an
really make sense.
This is the I component of the ijk.
We're not using IJK, or we're not using the IJK as a basis vector system.
We're not.
So we need to forget about
Okay.
that. This is,
I see. I
we'll
see.
totally forget about your old version of IJK.
Okay. Okay. I get it. 'Cause each number in addition to I is the next dimension. So, okay.
Right. So I is equal to 1, 2, and 3, and that by itself describes all 3 dimensions of your coordinate system.
Yep. Yep. I have it.
What did you guys come up with back there?
We get. I mean. So like I get it's a dot product of, or I mean A1 B1 plus A2 B2
Mm-hmm.
plus A3 B3. I am wondering how to like if there's this specific way you want us to represent it, or like some like.
Well, so you've got it that it's A1 B1 plus A2 B2 plus A3 B3. So if we want to represent this with, we still have an A and a B in there, and they're just going to be, you can get rid of the dot and you can get rid of the bars, but what do we need for I's and J's or P's and Q's or whatever you want to call it? To get this.
Isn't this AI times BI?
Yeah.
Oh, okay.
Because we sum over when it's doubled like that, and actually we could use AP BP. It doesn't have to be an I, but it's a repeated index, so we sum each of the individual components.
Oh, I thought the repeated index had to be on only one, like APP.
No, anywhere you see a repeated index.
Oh, interesting.
Anywhere. But you can never have a third repeating index. If you stick a third B in there, that's
Can you
impossible.
can you example the wrong example? Can you show what do you mean what?
Well, if you had like this.
Why would you do that?
Well, why? I don't know, because it doesn't exist.
Wait, could you
You
have
can't.
APP BPP?
Having BPP by itself is equal to B11 plus B22 plus B33.
Mm-hmm.
But having that third repeated index in there no longer means anything. It does not.
What do you mean if it had BPP, had 3 P's? You said that doesn't have any meaning?
No. You can't repeat over more than 2 indices.
Because you're limited to 3 dimensions. Because otherwise that the reason, or I'm missing something? Why can't you do B111, B222, and B333?
Well, you could, but you could write it out, but it wouldn't, it just doesn't have any meaning. It can mess up. It just doesn't work in
Okay.
these.
Okay.
You could write this B111 plus B222 plus B333, but it doesn't actually have any useful meaning for us.
Okay.
Yeah.
So the result of the problem 1 is 2xi plus yi equals to zi. Is that
Yeah.
Yeah.
okay?
This is that answer. And this one is that answer. What did you guys come up with?
Ci is equal to lambda bi.
So this one, let's use something different. Cm equals lambda bm. In this case, do we sum over these? There's repeating indices.
But it's on different sides of the equal sign, so no?
No. This is a vector on both sides of the equal sign. And all this is we're multiplying it by a scalar. So it's not changing anything except the length of that vector. And what'd you guys come up with for this last one?
dui over dxi over dxj.
dui over I over dxi. And then what?
And dxj.
And dxj. And how did you get that?
The Laplacian is the divergence of a gradient.
So this is dui or du1 du2 du3 and we have two of those plus the ui, but the key thing here is that we do have you can, that you are taking the first gradient, you have to have one of the similar, you have to be adding over one of those dimensions to get it to work because it's the Laplacian of the gradient. I'm just trying to think if there's a better way to explain why you have the two i's there.
The way I wrote it out was nabla dot product nabla u.
That's
That.
Yeah, that's a good way to think of it. Yeah, if this is just a nabla u, then this is dui. Actually, these are all i's, right? Jesus. Two, three. 2, 3, 1, 2, 3, or just dui, dxi. Is that right? Did we do that right?
I think the i's and the j should
The j should be in there. That's where you do have to be a little bit careful with these, so. But these are interchangeable, so you end up with the same result in the end.
it's an I or an J out of all this.
These are an I on top, one I on bottom, and one J on bottom. So, what are we summing over in this?
I.
The I. There's a J left over in the end. So is this going to be a scalar or a vector?
It's a scalar. No.
We still have a J at the end, no matter what we come up with. There's still going to be a 1, a 2, and a 3.
Okay, so then it's a vector.
Yeah. So if we sum over our i's, we're left with a J at the end. So whatever it ends up being, it's something that's got a J. Which means that it's a vector. So it is an easy way to know. You can easily figure out if you're going to end up with a vector or scalar or whatever by looking at however many indices that you have kind of left over. But again, it's for those of you that it's new for, it takes practice to get it right and to just be comfortable with it. So just be patient with yourselves if you What's up?
Excuse me, what is the name of the rule again?
Of what?
The rule of this overall
It's all called index notation.
Okay.
Or Einstein notation. So you can, there are little primers online in various places. You can look it up and look at the basics. But in terms of what we want to be able to do with this, back to our stress guy. Do you remember I said the stress has a magnitude and how many directions associated with it? 2. So the tensor, you can actually use the tensor so if we take our concept of a stress tensor, which has a magnitude in 2 directions to it, and we
Hey, I see a repeated index.
do, yes. Awesome. We multiply by a normal vector, so this might be the surface that we're interested in, knowing what's happening on the surface. So the stress tensor it's everywhere in that box. But if we actually want to know what's happening at a specific place or a specific orientation of that box, if we have a fault and we want to actually know specifically what's happening on that fault. We know there's a fault through here. Of course, the stress tensor box is infinitely small conceptually, but we can draw it this way. And say we know this is our earthquake situation we're looking, this is a map view, we're looking down on the San Andreas fault, say. We look at the bigger picture and we're like, well, we know there's a regional stress that's shearing like this. But we want to figure out what that shear is on this fault. But the data we have has the shear in this other orientation. Do you guys see that question? Basically, we want to know, well, how does this shearing get translated to what's happening on this particular fault? We can take the the normal to that plane, write out our stress tensor, multiply these two, and come up with this, what we call the traction vector. I use T because we call it the traction vector often. This big scale shearing it might end up well, let's do this. It's going to have some kind of a component of shearing across this fault, but it's now rotated a little bit. But it might, this regional stress might actually also induce some compression across that fault. So this big scale stress state, we want to know specifically what's happening on this plane. If we do this, we'll get a vector that actually is the sum of the shearing force and the compressive force. So it'll be a, well, let me draw it in a different color. It'll be easier. If you were to draw it out as a vector, because it's a vector sum, but we usually end up dividing it up. T has a normal component and a shear component, which is, and so these are vectors. So you have to be careful with these because they're more like the forces that you're used to thinking about, but you really can only derive them by putting it in the concept of the stress and then picking out a specific plane that you're interested in. So we don't always go around and talk about a specific traction vector as a force, because it doesn't, you have to be careful in terms of translating it from one problem to the next. And it's only that vector if this is the plane. If we rotate it, then this vector is different, which is why you have to be careful. You can't just say that this red arrow is the way the stress always is, because if you had a different fault, the stress would be different on that fault. Same overall stress region, but how it actually gets applied in terms of a normal and a shear on a specific plane depends on the plane that you choose. So this is why the stress is the universal thing. The specific action on that fault is different for every fault. So this is what will stay the same. If we can put in any plane we want, we can figure out what the shear and the normal components on that plane are. Does that concept make sense? And literally how we would do it, if we knew, say our sigma ij just has this one sigma 1 3 sigma 3 1 T1 T2 T3 N1 N2 N3. You can turn it back into a linear algebra problem if you want to try to solve it. And what does this look like? T1 equals, well, sigma 1 3 n 3 0 N1 sigma 3 1. Is that right? That's right. So if we solve this problem, you take N1, N2, N3, dot them in there, but only these two components are there. This one's all 0, and that one is N3 down there. So you can figure out what the T1, T2, and T3 components are in this big coordinate system that you've defined. So you still have to remember that you've got your 1, 2, and 3 coordinate system. So T1, 2, and 3 are the expression of the red vector in this 1, 2, and 3 coordinate system. You might then have to, when you want to figure out what the exact shear is on that plane, you have to then rotate the coordinate system of this vector to figure out, to figure out the component in this direction and the component in that direction. Because right now it's written in terms of this big coordinate system. But that's, so you would take this coordinate system, this vector in this coordinate system, this plane in this coordinate system, and if you dot them, you can figure out the projection of that vector onto your new coordinate system. Is this kind of remembering from vector calculus how you would take the components in one direction in one vector in one coordinate system and start to think about them in a different, or doing the dot product to figure out, or you can do a dot product between any two, right? And that whatever your overall coordinate system is, you can figure out the projection of that vector along the other vector, the direction of the other vector. And it's just the dot product that will get you that. So this is probably digging deeply into some of your memories. Hopefully some of it is starting to look familiar, even if we're talking about it in different terminology. But you will, in your problem set for this week, actually go through this exercise. Take a stress tensor that's like a regional stress tensor that'll look something not much maybe slightly more complicated than this one. You'll pick N1, 2, and 3, that'll be your fault. You'll come up with the traction vector within the bigger coordinate system, and then figure out what the normal and the shear component are on that fault. And then you can figure out if the fault might slip. Depending on, because if the normal force is really high compared to the shear force, does anyone with their geology background remember how we decide if a fault's going to slip? If we are it obviously wants to slip under that shear. So if we had no normal force, it would slip along here. And what is that slip then? What's happening at this boundary that will allow the slip really to happen or not? What's going on there?
That's friction.
Yeah, there's friction there. How does friction behave when you add compressive stress to it?
It increases.
Yeah,
It's proportion. The force is proportional to the.
Right. So if we have a tiny bit of a normal force, even with the same shear, it'll be a lot easier to slip than if you have a really big normal force. You can prevent that fault from slipping because you've got this huge normal force holding it together and the friction is too high. So so now that you have your normal and your shear components of what's acting on the fault, then you need to figure out, well, what is the friction coefficient and how is that going to vary, and is it going to slip or not? based on that. What happens to a fault if you start injecting water?
Slips more easily.
Yeah. So if you have a system where you end up getting a lot of a high pore water pressure or something within the rock or along the fault, then it's got a higher likelihood to slip. That pressure, you increase the pressure of the fluid within the fault. Pressure is a stress in every direction, right? But the pressure what it's really doing is counteracting this normal fault. So the component of the pressure that's doing all the work is the one that's going against that normal. So you can pump a lot of fluid in there and cause a fault to go, which is what's happening in Oklahoma with all the hydrofracking and the earthquakes that's setting off, because they're pushing fluid into all of these cracks in there, probably ones that they didn't know that they didn't know were there. They didn't change the overall stress in the region, but they did change the fluid pressure along the faults, probably some unknown smaller faults within there, which is making them slip when they didn't slip before. So, does that make sense? Hopefully this is starting to come together. Tuesday we will have a discussion. This paper, which is about continents deforming, we'll have a discussion about this paper in terms of how it's a review paper on the idea of how to take some of these ideas and continuum mechanics and apply them to continental deformation. So that'll be like a half an hour or so of the class on Tuesday. And Monday we do have the computing assignment, which I am trying to revise from the last year's one because it's not quite done yet. But I did post the problem set, so you can download and look at that and get started on that.
The problem set for the lecture
The whole
assignments?
unit. The whole
Okay.
unit. So it's not due until until 2 weeks. Due like the 25th of September. So you have a full week after the end of the unit to finish it. Any last questions? I think there's a meeting in here right now, so I'm gonna get kicked out. And let me know, email me if you have any questions. And I'm happy to meet with people on Tuesday or Wednesday of next week if anyone wants has some extra questions. I don't have terribly regular office hours because my schedule kind of varies a lot, but generally if it's a short question, and you find me in my office, you can poke your head in anytime after noon though, because I like to be able to set my mornings for focusing on like writing and stuff that I need blocks of time, and it's harder to be disturbed. But if you have a longer question, just send me an email and we can set up a time, and we'll happy to discuss it with you.